Hello everyone, welcome to this lesson. So in this lesson we're going to cover the third order and fourth order Runge Kutta methods Python codes. Now to recap briefly, we have discussed that actually the Euler's method was in fact a first order Runge Kutta method. The Hans, Midpoint, and Ralston methods were in fact a second order. And we have discussed also the third order, that the third order involves three derivatives to describe how the derivative is changing within each interval. And we have described K1, K2, and K3. And also with the fourth order, instead of describing the interval with 3 or 2 or even 1, we're describing it using 4 different derivatives, one at the start of the interval, one at the end, and 2 at the midpoints. So let's actually begin. So with the third order Runge, it's actually defined generally this way: yi plus 1 is equal to yi plus 1/6 multiplied by k1 plus 4k2 plus k3, all multiplied by h, where k1 is the derivative at the start of the interval and k2 is the derivative at the midpoint using k1. So you can see this is Euler's method using k1 evaluated at h divided by 2, so evaluated at the midpoint. And if you see k3 is also still the derivative at the midpoint with xi plus h divided by 2, but the y now is defined using this expression where I am giving -1 weight to k1 and 2 weight to k2. So let's actually begin. So much like with the previous codes, we're going to be importing the math and importing the matplotlib for later visualization. We're still dealing with the same equations. The derivative is sine x squared multiplied by y. Here we still have the exact solution for this derivative. Initialization is still identical. We're still dealing with the integration interval of 0 to 5 with a step size of 0.5. Here we use this information to calculate n. Here we also have the initial condition of y equal 2 at x equals 0. This is an identical visualization code with the print functions. Here's the header, and also here is displaying the first values for the x, y, and the corresponding also true values. So the slight difference that I have here from previous codes is now I'm actually adding the true value as the third column. So here f of x in the header, and also f of x here as well. So let's actually go to the main code. In this code, you're going to find that it's actually very, very simple. The first line of code here is to just capture the x, y, and the f of x for the visualization. Here we have 3 lines of code, k1, k2, and k3, to calculate the 3 derivatives to describe each of the intervals. The first k1 is calling the dy function and evaluating x and y. So this is the derivative at the start of the interval. K2 is evaluating the derivative at the midpoint. You can see the x value is x plus h divided by 2. And here the y is defined using Euler, using k1. So basically this equation here is identical to what we have here. X3, still the x value is at the midpoint, x plus h divided by 2. And here's how we're describing the y minus k1 multiplied by h plus 2 times k2 multiplied by h. So now that I have k1, k2, and k3, now I can plug it into the main equation for the Runge Kutta third order. So y is equal to y plus 1/6 multiplied by k1 plus 4 multiplied by k2 plus k3, all multiplied by h. So now that I have the y, I get the corresponding x. So it's going to be x equal to x plus h. Now that I have x and y, I can now print x and y and the corresponding true value to create the table. Now the visualization code here is identical to the ones that we did before. So to recap briefly, the first line is to capture the last x and y values here. And here we are calling plt.plot. The first x and y here is for the Runge Kutta. I'm also giving them a theme of solid red circles. And here the second xy is the xy for the analytical. Here also added labels, x and y labels. And here the legend, we have Runge Kutta third for the first xy and analytical for the second xy. So let's actually run the code. So I'm going to import the packages. I'm going to run the functions and I'm going to run the code. All right, perfect. So we can see the x values 0 to 5 with here a step size of 0.5. Here are the Runge-Kutta third order y values. Here are the true values. And you can see it's actually a really excellent approximation for the analytical solution. It almost captured, of course, the trend, but it also captured almost the true values. So if you look at here, is 2.05, here is 2.08, 2.536, 2.627, and 3.91, 4.87. So you can see very similar numbers to the true value. So now that we have seen the Runge-Kutta third order, how about we go and see the fourth order Runge-Kutta? Now, if you remember for the last lesson, we have described the fourth order as yi plus 1 is equal to yi plus 1/6 multiplied by k1 plus 2 multiplied by k2 plus 2 multiplied by k3 plus k4 all multiplied by h. So we have described the four derivatives. If I take, say, for instance, this interval, I'm going to take the derivative at the start of the interval, and that's going to be k1, then the derivative at the midpoint, k2, and I'm going to calculate using k1. Then I'm going to get another one at the midpoint, but this time I'm going to be using k2, and then the last one I'm going to get k4, which is the derivative at the end of the interval, and I'm going to use k3. So I'm using all four of these derivatives to get what this y point is going to be, given how the derivative is changing within this interval. So here we can see that the importing of the packages is still identical, functions is still identical to the previous code, initialization is still the same, visualization is still the same. So let's actually go to the main code. Here still we have the line that is going to capture the xy values for the visualization. So you can see that the main difference between the Runge-Kutta third and fourth is really the definition of the derivatives in the main equation here. So k1 is still the derivative at the start, k2 is the derivative at the midpoint, but now I'm describing it using here y plus k1 multiplied by h divided by 2, and you can see that k1 and k2 for the Runge-Kutta third order and the fourth order are identical. So you can find that the difference lies in how we define k3 and k4. So k3 is still the derivative at the midpoint, x plus h divided by 2. Y is now defined using Euler, y plus k2 multiplied by h divided by 2. And the last one, k4, which is the derivative at the endpoint, which is going to be x plus h, and here y plus k3 multiplied by h. So once I have k1, k2, and k3, and k4, now I can plug him into this main equation. Y is equal to y plus 1/6, k1 plus 2 multiplied by k2 plus 2 multiplied by k3 plus k4, all multiplied by h. Given that I have y, I get the corresponding x. X is equal to x plus h. Once I have x and y, I can print them out to create my table with the corresponding true value. This visualization code is identical to the other. The only difference is now I'm defining it in terms of Runge-Kutta 4. So here RK4, here also RK4, and also the legend RK4. And don't forget also with the list for the visualization to be defined in terms of RK4 here and here. So actually, let's run the code. So I'm going to run the packages and the functions and also this code. Now, you don't really need to run the packages and the functions since I already ran these with the previous Runge-Kutta, but if you have this in a separate Jupyter notebook, for instance, you would need to run them. So let's actually look at it. So you can see it's excellent approximation for the true values, almost identical to it. You can see that the red dots are almost superimposed to the analytical curve. You can see here we have x values 0 to 5, increment of 0.5. These are the Runge-Kutta. These are the true values. So actually, let's see how the numbers compare. So if we look at the second value, 2.08, 2.08, 2.6265, 2.6269, 4.86, 4.086, 4.087. So you can find that the numbers are very close. So compared, this is the Runge-Kutta fourth, and if I go back here, these are the Runge-Kutta third. So we got an even more excellent approximation for the this differential equation using the fourth order, which is why actually this is the common technique used to solve ordinary differential equations. Then you can see of how effective it is. Now in the next lesson, I'm going to be running through a few examples of differential equations and apply the Euler's method, Hans, midpoint, Ralston, third order and fourth order, because I want you to see how the approximation visually changes as we're actually increasing the order of the Runge Kutta. So that's it for this lesson, and I will see you in the next lesson.